So my name is Steve Ackerman. I'm here at the University of Wisconsin, and I'm the director of the Cooperative Institute for Meteorological Satellite Studies, which is a collaboration between NOAA, primarily the NESDIS, the satellite branch of NOAA, and the University of Wisconsin. And we have actually about 8 NOAA employees stationed here, working with us mostly on, as the institute name implies, meteorological satellite stuff.
And I'm Margaret Mooney. I also work here at CIMSS at the University of Wisconsin-Madison. And I used to work for the National Weather Service here in Madison for about 15 years, but now I'm an Earth Science Outreach Specialist at CIMSS.
And she's interested in working and reaching out to you storm spotters to try and get something going collaboratively with regard to what's happening in Wisconsin with regards to our weather and climate. And so that's what we're going to be talking about today, except I don't seem to have control over my, there it is. So we're going to be talking about climate change in Wisconsin and the Great Lakes region with a focus on doing two things. One is talking broadly about what's going on globally, and then switching into more regional impacts, specifically changes that are occurring in Wisconsin. And I'll talk for about the first half or 2/3 of the presentation, and then we'll be switching it over to Margaret. So a lot of the information that we're getting is, I think my thing is going a little slow. All right, so you all are weather geeks just like us, and so you clearly know what weather is. And I just wanted to put this slide up because there are a couple of different definitions of climate. One is right up there at the top of the page. Climate is what you expect. Weather is what you get, kind of a flippant definition. A lot of times we also hear that climate is just the average weather conditions, which is an okay definition as well. I like to think of climate as the following definition at the bottom of this: the collective state of the atmosphere for a given place over a specified interval of time. And there are 3 parts to that definition. So there's the definition. One is location. So this is why I like this particular definition, because it tells you that when you're talking about climate, you have to talk about the location. Are you talking about the globe and the changes of global conditions, or are you talking about a particular region like the Great Lakes or a particular city like Madison? And so as I go through this talk, I will be identifying the location that we're talking about. It also talks about time. As we well know, climate, as we begin to take averages, is a function of how big that climate averaging time scan is. Usually, NOAA in particular looks at 30-year averages, so 30-year temperature means. But clearly, if we're going to be looking at the Earth's history, 30-year averages are too small. And so we look at averages over centuries or so. Most of what I'm going to be showing today are associated with those 30-year averages. And then the third thing in the definition is about the variables, and that it's not just the averages of a particular variable, but it's also looking at the distribution about those averages, or the extremes as those. And we'll be showing you some of those examples for at Madison and Eau Claire later as well. So looking on the large scale, so first we're going to again look at the global scale of what's going on, because sometimes we get questions about that. And then we'll go from the global down to the regional, into the Wisconsin. So this map right in here, I'm assuming you can see my cursor. I'm now waving it over by the y-axis. What we're looking at here is the global mean temperature, and each one of these dots represents the annual average of the global temperature as determined by surface observations. On the right-hand side of the y-axis is the estimated actual global temperature, where 14 degrees is about 57 Fahrenheit. And on the left-hand part of the y-axis, we're looking at what is the difference in the global mean temperature from the 30-year average, 1961, to 1990. And this difference, later on, you'll also see me show plots where we talk about the difference as the anomaly. And that's all the anomaly is, it's just a difference. So a lot of variability associated with natural variation, associated with changes in weather for any particular year. And so that's why the black dots are all over the place. In order to eliminate some of that variability, we tend to smooth the data by doing like 3 or 5 year averages, and that's what this thicker blue line represents. And then the lighter blue line or area represents the variability as we do those averages. And again, you can see this is running back from about 1850 all the way out to about, I think this is going out to about 2005, 2006. The different lines on here are different analysis of the trends. So again, looking at the red, so going back over a 150-year time period, if we were to fit a line to this, you would see that indeed global temperatures are rising in comparison to what they were in the 1860s. The purple line represents 100 years, looking at the last 100 years. Orange line, 50 years, and the yellow line, the last 25 years. And as we go to those different averaging periods, you can see that that slope is getting steeper and steeper, which is telling us that the change is occurring more and more rapidly. We really can't get below about 25 years in these averages because then these trends are no longer statistically significant. So sometimes people may pick 2 years and then look and say, look, the actual global mean temperature is decreasing. But you really can't look at 2 years because that's not a statistically significant way of looking at it. And so by the time you get to a 25-year time period, any shorter than that, then you're going to run into problems with significance because of the natural variability that we see all the time. So indeed, this has led to the conclusion that, yeah, the Earth is warming up. And this graph was actually from the IPCC report, the International Panel on Climate Change, which we'll talk a little bit about later on. The IPCC concluded, as we'll see later, that the warming is unequivocal. And the other thing that we look at when we're looking at global climate change is not just are we seeing a trend in a parameter, but we're also very interested in seeing if we're seeing a global mean temperature rise, then that means that we ought to be seeing other things as well. And what this plot is showing us is the relationship between these parameters. And there are many other things we want to look at, but in this particular case, the first thing that we look at, of course, is this is the figure we were just looking at, that there is a rising temperature change of the surface air temperature, right? That's generally going up. So we're also seeing a warming of the oceans. And if we expect to see a global mean temperature increase, and then as the oceans warm, then the water should thermally expand. And so we would expect to see that the sea level rise should also be occurring. And that's what this figure is showing us. Again, each point here represents a observation over the year of the average sea level. And then again, the blue envelope represents our confidence in the data. And so again, when you're going back to the 1870s or so, you know, we have less confidence in that data because we didn't have as many measurements. But as we get in time, we're getting more and more observations, and our confidence gets better and better. And indeed, this red line up here is actually satellite observations, so we're seeing real global trends, observations, I mean. And so, yeah, again, what do we see? A rise in the sea level. And again, this scale is about, is in terms of millimeters. So again, consistency between global mean temperature, that's going up. We ought to see an average increase in sea level, and we're seeing that. The other thing we might expect is if the global mean temperature is going up, then snow cover should be going down. And so this final curve in here is looking at the snow cover area from the northern hemisphere. And of course, that record does not go back into the 1800s. It only goes back to about 1920, 1930s or so. And again, if we look at that, again, we get a lot of variability. We're all weather nuts, and so we know that from year to year there's a lot of variability in snowfall. But what you can see in particular is that around about 1960s or so, there is a general decrease in the amount of snow cover in the northern hemisphere. Prior to that, it looks like there was a lot of variability, and it didn't seem to change very much. But in the last 40 years or so, we've seen a decrease in the northern hemisphere snow cover. There are a lot of other evidence that suggest that all of this is real. For example, along with ocean warming, we would expect it to absorb more carbon dioxide, and therefore that should make the ocean waters more acidic. And indeed, we're seeing that as well. And generally, again, if you take it a step further, more acid ocean means we ought to see a change in coral reefs. And we're seeing a change in the health of coral reefs that go along with that. Another example that we often hear about is the Arctic sea ice extent. So again, going back to 1980, prior to that, we don't have really good observations. And so again, looking at the ice extent anomaly, so the difference from a 30-year mean, usually around this 1990 time period. And again, each dot represents the annual average aerial extent. And then again, a lot of variability as we would expect. So the blue line, the solid blue line, is again a smoothing of that. And if we were to fit a trend line to that, again, that's the dotted blue line, which again shows us that in the northern hemisphere, the sea ice is, the amount of sea ice that we're getting is already decreasing. Of course, as we note down here, that's not going to add to the increase in sea level rise because the ice is already in the water. What's contributing to the sea ice, what's contributing to the sea level rise besides thermal expansion is as we melt land ice, like glaciers in mountains and things like that, or on Antarctica or Greenland. So what drives this observed warming? Again, we see the observed warming. We see consistency in observations of other parameters. So now we have to be asking ourselves, you know, what's the physics behind this? What should be causing this? And of course, the answer to that is increases in greenhouse gases. And the one we most often talk about is carbon dioxide. So we're looking at the concentration of carbon dioxide in parts per million molecules in the atmosphere. And again, now, once we start looking at carbon dioxide concentrations, if we start looking at air bubbles, for example, trapped in glaciers, we can analyze those bubbles and actually figure out how much carbon dioxide was in the atmosphere. So instead of just going back to the 1880s or so, using this proxy data, we can go all the way back 10,000 years or so. And as we look at that, we see that, yeah, there has been some variation, but as we, again, look into this zoomed-in gray area, going back to the Industrial Revolution time period, we can see that there has been a general increase in the amount of carbon dioxide. And particularly since about the 1950s, there's been a rapid rise in the amount of carbon dioxide in the atmosphere. And if we look at the amount of carbon dioxide that's getting into the atmosphere, in addition to estimates of how much fossil fuels and wood that we're burning, we're seeing that this rise is very consistent with the amount of burning that we're doing. Of course, carbon dioxide is not the only greenhouse gas. Methane is another very strong greenhouse gas, and we've seen rapid increases in that in the last 50 to 100 years. And nitrous oxide is also a greenhouse gas where, again, we're seeing some unprecedented rises in the last 50 years or so. And all of these three that we're listing here are due to human activities. By our just living, we generate these types of greenhouse gases that get into the atmosphere. And again, these figures are from the Intergovernmental Panel on Climate Change. And again, what that group does, I'll say this now and we'll probably say it again later, is they don't actually do any research. What they do is it's hundreds of scientists and politicians and industrial folks who get together and analyze the data that's out there and bring it together. And so they've brought a variety of measurements from a variety of folks and have kind of composited into one report, or actually a few reports. So again, what we're seeing here is basically correlations. We're seeing increases in CO2 and we're seeing rising temperatures. But again, we always want to be asking ourselves, it's not just about the correlation, it's the causation. And so how does carbon dioxide and these other trace gases lead to a global warming? And the answer has to do with energy gains versus energy losses in a system. And so if your energy gains into the system exceed your energy losses, then you're going to heat up. And if your energy losses are greater than your energy gains, then the system will generally cool down. And so when we look at the Earth as a whole, as a system, if Earth is the system, then our environment is space. And so we have to look at the energy gains and energy losses with regard to space. And so we get our energy gains from the sun. And the thing about greenhouse gases is they're like windows. Basically, you can add a greenhouse gas to the atmosphere, and that's not going to lead to an increase in the amount of solar energy that the atmosphere absorbs. So the same amount of energy is going to hit the surface. Surface heats up, and anything with a temperature emits energy. And as that temperature gets warmer, the more energy it emits. And so the Earth's surface continues to emit energy upward. Some of that escapes out to space, and some of that energy, and in fact most of it, is actually absorbed by the atmosphere. So if we add a greenhouse gas, like carbon dioxide, solar energy still streams into the Earth's surface, warms the Earth's surface, the Earth emits energy out to space. The increased carbon dioxide actually absorbs more of this energy emitted by the Earth's surface. And again, of course, that energy increases the energy gains of the atmosphere, so the energy gain leads to a warming of the atmosphere. Of course, the warmed atmosphere means it emits more energy out to space, but it also emits more energy back down to the surface, increasing the energy gains of the surface, warming the surface. So the surface warms up more, emits more energy to the atmosphere, which the atmosphere warms up. So we end up getting into a cycle or a feedback mechanism here as well. As the atmosphere warms, it warms the Earth's surface further, and that can increase the atmospheric temperature as well. So the physics of understanding the relationship between the greenhouse gases and the global warming is pretty well understood. Of course, it's a lot more complex than just that simple argument that I made. There are, of course, other feedbacks that occur. It's not just the carbon dioxide. And the biggest feedback is what happens to the water vapor. So I talked about how the atmosphere warms up. It emits more energy back down to the surface and warms the surface up. But in addition, as the atmosphere warms up, that means the saturation vapor pressure is going to go up, which means there can be more water molecules in the atmosphere. So we actually increase the water concentration in the atmosphere. And of course, water is a natural greenhouse gas. And so by adding more water, we again increase the greenhouse gas of the atmosphere. And of course, what happens is we begin to affect this entire hydrological cycle, as represented by this nice diagram, which actually represents what's going on in the upper Midwest. So you can consider this as Lake Michigan. Here's Milwaukee, or I guess you can think Chicago if you're in Illinois, where again, they're looking at exchanges between putting wastewater into the lakes as well as taking drinking water out of the lakes and, of course, cleaning it before distributing it to people. But the other thing, of course, is that as we increase more water vapor concentrations in the atmosphere, that provides more water molecules for precipitation. So again, we could be affecting precipitation patterns as well. And we'll be talking about that in a little bit as well. So it's not just the temperature, which is what we've been focusing on, but it's other weather variables as well. So again, want to emphasize that the observed warming that we can see is also consistent with other observed changes that we would expect in a warmer atmosphere. So again, atmosphere warms up, we would expect to have a retreat in non-polar glaciers on land, and clearly we're seeing that, right? I mean, I know a lot of people have told me that I should go see the glaciers in the Rocky Mountains before they're all gone. Arctic sea ice has thinned 40% in the last decades, and its extent has decreased by about 15% in the spring and the summer in the 1950s. We still have sea ice up there in the wintertime. We just have less of it, particularly in the spring and the summer. As we showed on the earlier figure, the Northern Hemisphere snow cover has decreased by about 10% since the 1960s. We'll see some more of this later on, but the growing season has lengthened by 1 to 4 days per decade in the last 40 years, particularly in the higher latitudes in the Northern Hemisphere. The growing season, of course, is that time period of which you don't get frost, and we'll look at more detail of that for Wisconsin. Duration of ice cover on lakes has decreased by about 2 weeks, and this is, we'll look at the Great Lakes in general, as well as one of the lakes in Madison, Lake Mendota, but we're seeing this in inland lakes all through the Northern Hemisphere. And you can imagine if you're an ice fisherman, you know what the impact of that is. And as we showed earlier, the global mean sea level has risen, that are associated with this warming as well. So again, it's not just the fact that we're seeing evidence that the globe is warming, it's also the fact that these other things that are happening that are very consistent with it, that makes the whole science picture complete. So we kind of see the observations. Physically, they're connected. They're what we expect. But of course, we want to still be able to explain it. And another way we tend to do explaining climate change is to use climate models. Much like we use weather prediction models to look at what's going on with the weather and understand changes in the weather, we use climate models to do the same thing. So the figure I'm going to show here is looking at the temperature anomaly, or the temperature difference between a representative 30-year average, going from 1900 to about 2005. And again, these are just the observations. Now, these are the smooth observations averaged over a 3 or 5 year period. And what we want to do is try and replicate this with our climate models. And of course, there are many, many different climate models. So if we take the climate models and pretend that humans are not alive, right? We don't exist. That the only changes we can have are due to changes in the solar output or changes to things in the system, like increasing volcanic activity. We can use the model simulations to look at what that impact would be, right? This is our laboratory, right? Weather models are the weather laboratory, climate models are the climate laboratory, because we can fix one thing and see what the impact is. So this blue line I just put on, these are, each one of these thin blue lines represents a particular climate model. And just like we have different weather models, we have different climate models. They do things a little bit differently. And then the thick blue line is the average. And again, this is for the case where we only have natural forcing, pretending humans don't exist. During this time period, of course, we've had at least 3 major volcanic eruptions. And what we can see is shortly after that eruption, we see a drop in the global mean temperature. And of course, that's occurring because the volcanic ash reached the stratosphere. And so it reflects solar energy out to space. Less solar energy gains, the system's going to cool down. And that's exactly what we see happening here. Of course, these are just the natural forcings only. Now that we know what's going on with the natural forcings, we can put humans in. And you can see we want to put humans in because while the natural forcings are, one might argue that, you know, they're doing pretty good prior to 1960. By the time you get past 1990, the natural forcings just are not matching what we're observing to happen. So if we put in human activity, so we go back and look at those curves for the increases in carbon dioxide, increases in methane, increases in nitric oxide, and make that part of the model simulation, this is what we get. So now again, all the yellow thin lines are simulations from a particular climate model, and then again, when we average them all together, you can see that is represented by the thicker red line. Again, you can see the impact of the volcanoes, but indeed what happens when we put human activity is we certainly get a much, much better match of what's occurring since about 1980 or so. So doing this over time in many different areas has led the International Panel on Climate Change to conclude the following things. And again, you could look at the historical documents, but in their report of 1995, so that would have been like over here in the time period, which means that they were really looking at science publications that were done in the prior to about 1992 or so. And what they were concluding as a body was that there's a balance of evidence suggesting that there is discernible human influence on this global warming. By 2002, our models are getting better, our observations are getting better, and we're getting more observations. So this panel, which again has not the same members go in and out, they're now concluding that most of the global warming of the past 50 years is likely due to human activities. And they actually define what likely means, and that means it's an odds of 2 out of 3. Certainly something I would bet on if I were in LA. I mean, not LA, Las Vegas. And by 2007, the report is now saying most global warming of the past 50 years, very likely, odds are 9 out of 10, that it's due to greenhouse gases. And I suspect now that the IPCC is beginning to collect data again for their next report, which I believe is due out in 2013, I suspect they're going to be saying that it's even more likely. So we have a question. Is that what somebody said?
No question.
No question?
No question. Yep. Brian, do you want to ask your question? Maybe he's muted. His question is, are humans to blame for global warming, or could global warming be natural?
Yes. I think, you know, what this figure here certainly demonstrates is that the humans are playing a role, that it's very likely that human activities are causing the global warming of the last 50 years. So now let's switch to regional climate. And a lot of what I'm going to show you now is coming out of 2 reports, the Global Climate Change Impacts of the United States. They broke this down by region by the U.S. Global Change Research Program. So again, this is just scientists from the U.S. And there's a report for the Midwest region, which is a great report, which I recommend if you're interested that you go get it. In addition, we're going to be looking at what's going on in Wisconsin. And this is a report done by WICI, the Wisconsin Initiative on Climate Change Impacts. And they've looked at how the climate in Wisconsin is changing, as well as how that impacts other things like biology, what the impacts are, and then also discusses some adaptation type of activities. And we're going to be looking primarily at the changing climate aspect of it. And the thing I want to point out here is that a lot of the analysis with regard to the changing climate was gathered from data from the co-op stations. So people were actually contributing to this. So some key issues with the Great Lakes. Summers are going to get hotter, which means we're going to have probably more heat waves, and that's going to impact air quality as well. We're also likely to see an increase in precipitation in the winter and spring, and I'm going to give you some of the, the key issues, and then we'll look at some specifics going down the road. And more likely that when it rains, it's going to come down in more heavier downpours. In the summertime, we're actually going to probably have greater evaporation. And so what's the concern here is that we may be having more increased periods of floods as well as water drought. So the fact that we get more precipitation isn't always the best thing, right? It depends on how it comes and when it comes. Reductions in the Great Lake water levels, and that's clearly going to impact shipping, the way people live, as well as the ecosystems around the Great Lakes. Native species are likely to face more increased threats as the global climate and actually the regional climate changes. That makes it more favorable for certain pests to be moving in, and I think if you follow the news, we're certainly seeing that throughout the Great Lakes regions. And again, as we're seeing longer growing seasons, for a agricultural state, that at first sounds like that's a really good thing, and it certainly could be. But again, there are other things in agricultural that we need to be concerned about. For example, increased heat waves, and not just the longer growing season, but also what's going to happen to precipitation. And it's not just the amount of the precipitation, it's with also when that precipitation occurs. Here's again some of the observed changes for the Great Lakes, in particular looking at ice cover, looking at 1973 to 2008. And you can see that the general trend, while there's a lot of variability, there's a big trend in decreasing the amount of ice cover on the Great Lakes. And we're certainly seeing this on the inland lakes. I'll show an example of that in a minute. Of course, what that means is less ice on the lake means in the wintertime we have more evaporation. And of course, that leads to lower lake levels. Heat waves, 1995, I think if you were around this region, you knew we had a really bad summer heat wave that killed about 68 people in Wisconsin. It's our worst heat wave that we've had since 1848. And so there's indications that this is the type of thing we can expect in the summer. Future summers is more heat waves. Of course, the National Weather Service issues advisories with regard to that. And so again, this is an area where adapting to a change, is certainly reasonable to expect. I mean, certainly in the southeast, they get a lot of days with heat indexes over the 100, and they don't have a lot of people die. So again, people can learn to adapt to this type of change. But also associated with these higher summer temperatures, they promote more chemical reactions, more pollutions, more ozone in the atmosphere, which means air quality is going to go down. Again, that's something that if we choose to, we can adapt to, right, by just controlling how much pollutants come out of the things we use in our daily lives by each community. Flooding. From 1950 to 2006, Wisconsin, on a general, has become wetter. On average, we've gotten about 3.1 increases in annual precipitation. Of course, it's also not just precipitation, but how it comes. And what this figure is showing up here is for the Great Lakes, upper Midwest region, that we're actually seeing a 27% increase in the days with heavy precipitation. So again, now just changing our focus from the global, we talked a little bit about the regional. Now we're going to talk about specifics with regard to climate change in Wisconsin. Again, getting it mostly from the Wisconsin Climate Change Report from the wiki, and there's the website down there if you want to get that report. They have it in PDF format online. And basically, one of the punchlines that they have is that, it isn't necessary that Wisconsin is getting hotter, but rather it's getting less cold. And the way they concluded that was, again, instead of just looking at the mean temperatures, which are generally going up, they also looked at the daily maximum temperature and how has that changed in the last 57 years, and how has that changed with regard to season. So what we can see here is that in the winter and the springtime, there's been a real increase over the 57-year period in the temperature maximums in both winter and spring. But in the summertime, there's not much change statewide. I mean, there is some areas where you get a real decrease in the temperature maximum, and as well as areas where you get some increase. And actually in the fall, the maximum temperature over the last 57 years has actually decreased. So again, what we see here is that the greatest amount of warming, while we see it increasing on the year, getting warmer, the greatest is occurring in the winter and the spring. And then actually in the fall, there is actually a cooling with regard to the maximum temperature. So again, the variability part. Of course, we want to look at the minimum temperature as well. And so when we look at the minimum temperature over the last 50 years, how that's been changing, again, the red, now we see winter, spring, and summer. Lots of deep reds, which means it's almost increased over these 57 years by about 2 degrees temperature throughout most of the winter, spring, and summer. In the fall, again, we're seeing a mixture. It's actually cooling in some places and warming in other. But in general, throughout the state, what we're seeing is that the nighttime low temperatures are actually warming faster than the daytime high temperatures are. And that's why, again, people are often saying it's not that we're getting hotter, it's that we're getting less cold. Of course, another way to look at it, again, in terms of extremes, is how many days in each year has the minimum temperature been below 0 degrees Fahrenheit? And again, between this period 1950 to 2006. And what we find is that, you know, compared to 1950, we are now getting this condition of minimum temperatures below 0 degrees Fahrenheit occurring 6 to 24 days less frequently. Again, and as you might expect, in the northern regions of the state, it's occurring less frequently than in some of the southern regions of the state or the areas around the lakes. And again, looking at the extremes on the other end, we can look how many days each year is the maximum temperature greater than 90 degrees Fahrenheit. And again, what we're finding there is very little change. I mean, there's some light pink and some light blue, but in general, throughout the state on the average, it kind of washes out. So again, the idea here is we're getting less cold as opposed to getting hotter. And then again, yet another way to look at it is what's happening with the date, the change in the date of the last spring freeze, as well as a change in the date of the first fall freeze. And in the springtime, that's occurring, depending on where you are in the state, a 6 to 20-day retreat. And in the fall, it's getting 3 to 18 days later. And what that impacts, of course, is the growing season. So the trend in the growing season over this 57-year period is that we now have 1 to 4 weeks of an increase in the growing season because of the warmer temperatures. Of course, looking at instrument records is not the only thing that we see changing in Wisconsin. Phenological observations also indicate that things are changing. So geese arrival, cardinal songs or robins. A lot of people talk about the first time they see a robin is a sign of spring. Well, that's occurring 9 days earlier now than it did back in the 1936 time period. And then the same thing with vegetation. People carefully monitor when they see their first blooms. I mean, the Cherry Festival in Washington, D.C. also does this, and they're finding that the bloomings are occurring earlier, both in the cherry trees as well as plants in Wisconsin as well. So what does that mean for us as we look to the future? Well, it doesn't mean winter is going to go away. And so this plot here I like a lot because it's a way to define winter as opposed to an astronomical winter, which begins on December 21st. What we're looking at here is the probability of, if it is precipitating on any given day, what's the probability it will be snow, which is above the dotted line here, versus the probability of it being rain. So clearly in the summer it's 100% probability of rain or 0% probability of snow. But somewhere around in Madison, this is for Madison, somewhere around the third week of November or so, we switch, and the probability, if it's precipitation, of being snowfall gets greater than 50%. So we can define that as winter if we wanted to define a meteorological winter. And similarly, we can get to the March in the latter, maybe the third week in March sometime, we also see that the probability of snowfall drops between 50%. So we can look at this blue line right in here, the blue shaded area, as our snow season or our winter. And again, each one of these thin lines represents the average probability for a given day, and then this is kind of smoothing out some of that natural variability. If we look to what the models are predicting, that's what we're going to get with this red line. And so again, you're going to see we're still going to have winter. We're still going to have snowfall in Wisconsin. We'll still be able to go skiing. It's just that the amount of time we're going to be able to do that is going to get shorter. And we can do the same thing for other states within Wisconsin, and certainly the Wiki report has done that. Here's what's going on for Eau Claire. Of course, they're further north than us. So again, their winter season is also predicted to shrink, although a little bit less than what we'd be seeing in Madison. Of course, this has impacts on the ecological and biological regions of Wisconsin. This is the pine marten. They got nice big furry feet. So when the snow is very deep and fluffy, they can walk along the top and get at their food source. Their competitor for that food source is, of course, deer. And so as snowfall goes down or it gets thinner, the deer have easier access to the food and can push the marten out of a given area. Ice duration on Lake Mendota. This is a lake in Wisconsin, of course, in Madison. And this is a well-studied lake, and it's looking at the ice duration, going back from 1850 all the way to the present. And each one of these observations represents a year. So we see a lot of variability, but over this past 200 years or so, well, not 200 years, 150 years or so, we can see that there's a definite decrease. In fact, we have 19 days less ice cover now than we did back in the 1850s. And again, looking at extremes, what do we see? The 10 longest ice cover days are all occurring before 1900. The 10 fewest days are scattered throughout the time period, but half of them are occurring since 1990.
Okay, so far we've looked at static graphs by and large, and I want to go online and show you an interactive graph from a group called Climate Wisconsin. Climate Wisconsin is a project of the Wisconsin Educational Communications Board, and it's got a couple of interactives, and it's got several audios and videos, and all the stories were supported by research conducted, which was in collaboration with that wiki group, the Wisconsin Initiative on Climate Change Impacts. So I'm going to go down here to an ice cover one. Whoops.
Hey, Margaret.
Yeah.
I think Kaylin Dom might have a question. She raised her hand when Steve was still talking.
Okay.
Kaylin, we can't hear you.
Oh, sorry.
Hi, Kaylin.
I was just wondering, if there's going to be shorter snow seasons, then why was there a huge snowstorm that hit Wisconsin and Illinois?
Yes, so the key is in that figure, when we're looking at snowfall cover, there's a very large variability with regard to year-to-year changes. And so when we talk about there being a shorter season, we're talking about averaging over a 30-year time period. The winter season is going to be less snowfall on average. But on any particular year, we could still get a record-breaking snowfall for a particular region.
So along with that variability, you remember the water cycle diagram where everything's kind of sped up, there's a little more energy in it. When the atmosphere is a little bit warmer, it can hold a little bit more moisture. So it's not surprising that some storms might be bigger when they do happen. You know, our winter season might be getting shorter. I mean, it has been observed to be getting shorter, but it's likely that the snowstorms are going to be heavier.
Yeah, we're still going to get a lot of snowfall. It just may not stay around as long.
Oh, okay.
So back to the wiki page, Climate Wisconsin. I'm online right now, and you can see the menu, which is just a bunch of pictures, and I'm going to pick the temperature, the ice cover one. And Steve just did the ice-off graph for Lake Mendota, which is a lake in southern Wisconsin in Madison. And I just want to show you this interactive. So it's going to graph the ice-on, ice-off dates from 1850 to 2010. So you can also ask it to show you the 10 longest seasons. Not surprisingly, they were in the earlier part of this graph. 10 shortest seasons. Most of them are more recent. And then even better, what's the trend? So we know from the data that there are 29 fewer days over the period of the record for ice cover on Lake Mendota. So that's, I think, a pretty cool interactive on the site. It's the same data that we were just showing you, and it's from the wiki report, and it's from mainly from the Wisconsin Climatology Office here in Madison, this particular data. Now I'm going to go to the other interactive on this page, which is temperature change. This data is from NOAA Cooperative Observers. And so you can see the graph on the left starts from 1960. And right now the one on the left is 2010. If I just put my cursor over any location, right now I have it over Marshfield. And in this 50-year time period, the average annual temperature has increased, and it's gone from 44.3 degrees Fahrenheit to 47.2 degrees. And so you can play around, and some of the differences might be a little less in that time period or a little more. But the other thing that's pretty cool about this is you can change the dates. So let's say you were talking to somebody who is only 10 years old or 20 years old, and you wanted to, someone wanted to see the temperature change in their lifetime. So for Madison in 20 years, about a degree and a half. We'll go to Milwaukee, a little bit less, but so the other thing that's interesting is climate projections. So this is climate modeling that Steve was talking about. I'm going to change the one on the right to mid-century, and I could go to year 2000, or pick any year I wanted, and see what sort of increase the climate models that the wiki scientists have run to see what sort of forecasts future climates will be like in Wisconsin. So I think this is a really cool, just look at the data, investigate it right away, a very cool tool. It's, you know, I think observed climate changes is one of the best ways to talk about climate change. Also, we're not going to do this now, but these videos are pretty amazing. They're like from 3 to 5 minutes long. Ice fishing in Madison, fly fishing in Viroka. Phenology, this is Nina Leopold. You guys probably all know Aldo Leopold. This is his daughter. She's 93, and she talks about documenting when they see certain flowers or birds. And she's been doing it all her life, and she compares her records to her dad. And they obviously note climate change is happening in Wisconsin. So now I'm back to the PowerPoint.
Hey, Margaret, we have a
Yes.
couple of questions.
Okay.
One from Brian Martinez.
Okay. Oh, a few.
Yes.
Brian. Well, how about Chad?
Yeah, and I think Chad.
Yeah. Can you hear me?
Yeah, now we can hear you.
Okay. One thing, I was watching University Place, and maybe that's later on in this presentation, but it was interesting. They were showing some climate change projections for Wisconsin, and the charts were like all over the map until they stuck a trend line on it, and you could clearly see the upward trend. This was on the University Place. You guys wouldn't have those. Are those later on in this presentation?
No, I'm not thinking. No, I don't think so. But I can imagine because they're probably showing, you know, they're probably not trying to reduce for the variation that one sees from day to day. And so then when they put the trend on it, they're kind of smoothing through all that.
Okay. Yeah. I was just curious because it was. I just found it very interesting because we as spotters we work with models all the time, and you know, there's always some ambiguity but it's interesting because I think sometimes people see raw data like that and they don't understand what they're looking at.
Right. Yep.
Yeah, we've also tried to stick primarily to observed changes and only mention the forecasted temperature changes, which is what this graph here is also about. But let's see, there's a couple more questions.
Brian, do you have a question, or maybe you already asked it?
Kaylin?
No.
Okay.
Okay. Well, I'll continue then. The wiki scientists downscaled climate models that the IPCC uses for Wisconsin, and they do forecast warming for our state. And by the middle of the century, statewide average annual temperatures are likely to warm by 6 to 7 degrees. And you can see from the little graphics that by 2030, our climate will be more like southern Illinois. So what can we do about it? Can we slow climate change or minimize impacts? First, two terms we use. Mitigation are things we can do to reduce the amount of global warming that's happening. Adaptation, Steve already talked about this, but it's a way to reduce the impact and adjust to what the changes that are going on. We have one more graph here from the IPCC, and it's climate models projecting the amount of temperature change based on our carbon emissions. So how much we mitigate and how much we adapt are going to be based on our actions. So about 5 years ago, NOAA and some other leading agencies came up with some basic principles about climate literacy, and they also had a guiding principle. And the guiding principle is that humans can take actions to reduce climate change and its impacts. Most of these actions have co-benefits. So one of the co-benefits is that if you reduce your energy use, you can save money. So most people need to look at their own household or their own lifestyle and figure out where they might be able to reduce energy use. This is just a little diagram about the average amount of energy used in homes. But if you can reduce your energy use, you can reduce your carbon emissions and save money. Or if you drive less or walk or ride a bike more, you can improve your health and save money. So did we mention saving money yet? But anyways, another co-benefit of driving less would be clean air. This is a natural experiment that happened during the 1996 Atlanta Olympics, where city government made everyone drive less. They just had restrictions on driving. And what they found out is that because the peak morning traffic decreased by 23%, the amount of ozone also decreased by 28%. And during that time period, the amount of asthma-related emergency room visits decreased by 42%. So this is a study. These two slides are from Jonathan Patz from the UW Wisconsin-Madison. He also was contributed to the wiki report. This next one is from him too. Another co-benefit of driving less is your own personal health can get better. So you can save money on gas. This is a study for an average bike commute in Madison. If somebody were to ride their bike every day, which some people here do, but they could lose some weight, but better yet, you could reduce the risk of heart disease by 47%, reduce the risk of stroke by 39%, reduce the risk of breast cancer for women by 34%, and reduce the risk for colon cancer by 43%, and reduce the risk for type 2 diabetes by 31%. So another way to look at a co-benefit is everyone's heard about reduce, reuse, recycle. One thing that is going on here in Wisconsin is recycling cow manure. So we have 28 plants like this in the state. The biggest one just opened last year in Dane County. And these tanks are co-located to the farms where they're going to get the cow manure from. And the manure produces methane, and it powers generators that create electricity. The one that opened in Dane County last year produces enough electricity to power about 2,500 homes. And that little graphic on the right, from poop to profits, there's a video about this. If you Google those exact words, you'll find the video. And you'll also find activity for teaching about it if you want to learn more that way too. So here's that guiding principle that the climate literacy group came up with, only applied to our area. Actions we can take today will reduce the impacts of climate change in Wisconsin, the Great Lakes, and beyond. This is two solutions, two ideas to mitigate carbon emissions. One is buy local. Just by the nature of geography, local products do not need to travel as far, so there's not as much fossil fuels being burned and not as much CO2 in the atmosphere. And also vote. Make sure you learn about candidates' positions on climate change and mitigating climate change, and then vote. So now we'd like to show you briefly about some other stuff going on here in our building. For about 10 years now, there's a guy here named Russ Dengel, and he created this software to show weather and climate data on a mobile phone, on a cell phone and mobile device. So there's a URL. If you're using your mobile phone, you can go online and type that in, and a whole list of products here that you could see. Now, if you did get a radar display, it would animate, so you can have animated radar. You can also learn a lot about severe weather from this menu. Satellite images. I have there on the bottom the convective initiation. That was from yesterday. So this is, the nickname is PAW, PDA Animated Weather, but this is one way to get real-time weather and climate on your phone. Coming this summer, we will have smartphone notifications working where you can get GPS-coordinated alerts for air quality, flooding, heat waves, and other events that are increasing in frequency due to climate change. You can sign up now, and there's a URL. And so you skip the www and just put wms.ssec.wisc.edu/notify. So it's actually working now, but we're still testing it. But that'll be working this summer. Next spring, the application will evolve so that you can actually enter reports into it. So finally, if you want to learn more about climate change online, we have 16 lessons at this URL. This course is a free course. We did develop it for middle and high school science teachers, but it's a good overall brief for anyone, and it explains a lot of the graphs we showed you from the IPCC report. It is also consistent with the climate literacy framework, and it was developed collaboratively by 4 departments here at CIMSS, the Atmospheric and Oceanic Science Department, the Geology Department, and the Center for Climatic Research. So that's what we had to show you guys today. We want to especially thank Rusty Capella for helping us promote this, and we wanted to thank Aaron from the Federation of Earth Science Information Partners for hosting the webinar. If you have any questions or comments, there's our emails.
Or we can take them right now, too, if you have some additional questions. And if you didn't get that poor email web address, we can put that back up, too, if you want to write that down. It's a great thing for handheld. Whenever I get stuck in the airport, I always go to it to find out whether or not it's really a weather-related delay.
And it's chat it to the whole group. You can do that, too. And I think now we have some questions.
Okay.
Chad?
Yeah, do you have me?
Mm-hmm.
Okay. Yeah, I really would like to put that up because I'd like the middle school students, actually middle school teachers, I'd like to give that address to them again. I have to get out of this. Yeah, that's it. I appreciate that. If you leave that up for just a little bit, my computer is freezing and I can't seem to. Okay, there we go. All right, I think I've just about got it. Data paw. Okay, thank you.
And if people want to put their hands up, I'll unmute.
And Kaylin, do you have a question, or is it just your hand up from last time?
That's from last time.
Okay. Hand's going to get tired.
I forgot to raise my hand.
Okay.
So I saw that reports that would have a spotter app. Is there any? I'm just wondering if there's any way that we could collect additional information that would be useful in this process, or just going through the normal channels the way we normally do. If that's good enough, or if you guys have ever said, you know, I wish we could do this. Do you guys have anything like that for us?
I think that is what is planned to be coming. So right now, by coming to this site, you know, we deliver data to you that you select. But we are exploring now. Again, this one is about notifying you of severe weather. But we are moving into this region where, in the lower right hand, where you can begin to put in reports that get recorded.
Okay, very good. I thought I saw that, but I'm busily trying to burn a DVD for some of my middle school students while I was doing this too. So I appreciate that.
Yeah, so we've designed, you know, just along those lines, an application where to validate our satellite-derived products of whether it's cloudy or not, an app for an iPhone that when the satellite's coming over, the phone will, you know, give you an alert that it's happening, and then you hold the iPhone up and you take a picture, and then you submit it to our website, and then it gets recorded, and then, you know, NASA can compare the iPhone image that you just uploaded to what the satellite algorithm or processing indicated. So yeah, we're
That's
going
really cool.
into that two-way interaction.
Cool.
Okay, I'm going to unmute the people that have called in on the phone, Steve, because I think one of the people with a question maybe.
That works.
Yep.
Okay, so all of our phone callers are muted, or unmuted. So Steve Fitz, you're on the phone.
Yes, hi. Oh, very good presentation you put together. Very educational. I had one thought. I came across a program on maybe the Science Channel where they're trying to capture carbon dioxide and to help reduce global warming. But I don't know how effective that is, and if you've heard anything about that, where they actually have a machine that sucks in the air and takes out the carbon dioxide.
Yeah, I've heard of programs, though I didn't think it took it out of the air. I thought it took it out of like power plant effluents, and then pump it. Essentially, they pump it into the ground.
Yeah. Is it possible to make a difference if they've put a lot of those?
Yeah, I think the big issue is that, well, pumping it into, one, it's expensive. That's the main issue, I think. But even after they get those costs down, what happens when you pump it into the ground is that it only temporarily gets there, and that there will be a time period when, again, it'll change from a storage in the ground to a source for carbon dioxide in the atmosphere.
That won't help, yeah.
Yeah, right. So it'll put it off a little bit, but not solve the problem.
Yeah. And then we still have the methane and the nitrous oxide or whatever that other gas was.
That's right.
From cars, yeah.
Yep. So I guess that might not work. Now it looks like from what your presentation showed that we're on an upward trend, and we probably passed that point of no return 10 years ago. Huh?
We're definitely on an upward trend, but we can slow how fast
slow
that
down.
trend is or how high it goes.
Yeah. Oh yeah. Well, thank you very much.
Mm-hmm.
Thank you.
Okay, so the next question is from Brian Martinez.
Can you hear me?
Yes.
Yep.
Okay. When we're talking about the global warming, so pretty much so far we can't go backwards. So this global warming, is it really like affecting the Earth as much as we're hearing it?
What was the last question? Is it what?
Is global warming affecting the Earth more than we think?
I'm not sure I would say more than we think. Probably. I mean, we really get a sense of what's going on with global warming and how it's affecting the Earth with regard to sea ice coverage, glacier, snow cover, precipitation, and things like that.
Yeah, because I heard from my science teacher that she says that if those ice caps melt from global warming, it will pretty much like the whole world will pretty much flood.
I wouldn't say it would be dead. It would certainly, if the ice sheets melt, like on Greenland and Iceland, that's going to be a really big issue for those who live on the coastlines with the oceans, because that will definitely increase sea level by at least a couple of feet.
All right, thank you, and good presentation.
Thank you.
So Kaylin had another question. Kaylin?
Well, if you happen to think of one later, I'll put our email up again, and you can just email me or Margaret and indicate that you were on this National Weather Service ESIP talk and had a question, and we'll reply.
Yes, and I think we're going to, we'll probably follow up once for those of you who gave us your email, follow up once with a short survey that we'd appreciate your comments. So thank you very much, everyone.
And thank you, Erin, for hosting this, as
No
well
problem.
as thanks to everyone else for listening in and asking your questions. And we look forward to potentially working with you all somehow in the future.
Thanks.
Thanks.
Bye.